Welcome back to the deep dive. Today we're getting really specific. We're going to unpack the data sheet for just one component, the NTI E-RTDS-PAR540-2IN pipe RTD sensor.
Right.
And our mission here is to figure out not just what it is, but why these very precise specs are so critical in industrial monitoring.
What's really fascinating here is that we're looking at, the building block of high precision monitoring. This is a 100-ohm platinum sensor, specifically the PT385 curve.
That 385, that's important.
It's critical. It defines the standard global resistance curve. That's what guarantees you can swap these out and that they'll be consistent across different systems. It's really the blueprint for precision.
Okay, so let's unpack the core function. This isn't from monitoring the air in a room. This is designed to clamp right onto a pipe surface, right?
Exactly. It's for direct surface temperature.
Right.
And the kind of thermal gauntlet it can run is pretty wide.
So what are we talking about range-wise?
Well, the operating range is extremely resilient. It's built for some harsh environments. We're talking from a chilling -58 degrees Fahrenheit
Wow.
all the way up to 540 degrees Fahrenheit.
That's a huge range. So -50 to 280 Celsius. It could be handling cryogenic lines or, I don't know, high-temp processing streams.
Anything in between, yeah.
Okay, but here's the part that I found most compelling. The accuracy specs. They get so specific, you just know that system integrity is, it's everything.
It is. They don't just give you a broad tolerance. They actually specify performance at these key reference points.
Like at freezing, for example.
Right. At 32 degrees Fahrenheit, or 0°C, the maximum error is rated at just plus or minus 0.54 degrees Fahrenheit.
Which is what in Celsius?
An incredibly tight plus or minus 0.3 degrees Celsius.
Plus or minus 0.3 C. At freezing, that seems extremely precise. Is that because you might be monitoring a phase change in a material? Or is it about regulations?
That's the key context. This kind of precision is absolutely demanded by applications in, say, pharma or food processing. A small deviation could mean an entire batch gets rejected. Or think about high-pressure energy systems, where you have to minimize thermal expansion. And even when you jump way up the scale to 212 Fahrenheit, the accuracy only expands a little bit to plus or minus 1.44 degrees F.
So that consistency across the spectrum is what you're really paying for.
That's it.
Let's talk about the physical design. The name says pipe-specific, and it looks like the design really backs that up. It's not like you're welding this thing on.
No, it's designed for a really easy installation. It has this adjustable ring mechanism.
Okay.
So it's versatile enough to fit common pipe diameters, anything between 1.25 inches and 2 inches. And it uses a reliable 6-foot 3-wire lead for connectivity to make sure those readings stay pure.
And it's RoHS compliant, I see. Currently listed at about $125.
That's right.
So you have this highly specialized sensor. How does it actually talk to the main system? I'm guessing you don't just plug it into a USB port.
No, that's a crucial technical point. It requires another component, the ERTDT-1562.
And what does that do?
Think of it as the translator. It takes that raw, delicate resistance signal from the platinum element and converts it into a standardized protocol. A signal that the bigger NTI monitoring systems, like the ETD or 5D, can actually understand, log, and send alerts about.
So it bridges the physical analog world to the digital one.
Perfectly put.
Okay, so we've pretty much established that this NTI sensor is a masterclass in specialization. It's defined by that adjustable fit for common pipes, and it's, truly pinpoint accuracy. That plus or minus 0.3 C tolerance near freezing really stands out.
Yeah, and this really raises a broader question for you, the listener.
Yeah.
Something to think about. If a manufacturer is investing this much in guaranteeing that sub-degree accuracy right on a pipe surface,
Right.
what are the hidden costs they're trying to prevent? Whether that's an environmental disaster, a production shutdown, or a human safety issue, the price of the sensor is tiny compared to the price of that data being wrong.